Okay, so chapter 14, number 61. We have this reaction here of A becomes B and C. And they want us to find the equilibrium concentrations for each value of K. So A, B, and C is giving us a different equilibrium constant. For each time, the initial concentration is going to be 1 for A, and we're not going to start with any products. So I guess the first thing we should do is let's write the K. So I don't like that. Let's do, Becca, what's your favorite color? Blue? You like bright blue or a darker blue?
Bright.
How's that? That's a pretty good K too, isn't it?
Yeah.
It is. It came out nice. You know, like it's hard to get like the straight line and the curved line to touch at the right point, but like they're like spot on. You guys really got to take some time to appreciate the smaller things in life. It's exactly how I wanted it. Do you want me to change it back? Okay. Because it's your birthday, I'm going to let this slide. Now, what is my expression here? K equals? Any squared or anything? Nope. Okay. Now what we need to do is this whole ice thing. Now, right now, you don't have to use a calculator. What's Q equal? 0, because I'm all reactants, no products. 0 divided by whatever is 0. So Q equals 0. So clearly, when my K right now equals 1, 0 is less than 1, I'm moving forward. So let's do a little diagram here of my concentration of A and B and C. Now, initially, what did it say my initial concentration of A was? 1 molar. What's my initial concentration of B? Yeah, the concentration of B. The, not number B, letter B, chemical B. It says the, right here, the reaction mixture initially contains, so what's my concentration of B at the beginning? 0. Okay? And now, my change. When I go from my initial to my equilibrium, I'm going to change. Now, is it going to have a positive or a negative change in A? Negative, because it's a reactant, right? And I'm going forward. Now, do I know how much of A I'm going to lose?
No.
No. So let's just do some algebra. I'm going to have a change of negative x. Now, if I lose negative x concentration in A, how much concentration is my change going to be in B? Plus x. Because, look right here, there's a 1-to-1 ratio. For every 1A I lose, I will gain 1B. Now, what's my change in C going to be? Plus x. Because it's also a 1-to-1 ratio. Now, to finish off my ice chart, ice's initial change equilibrium. Ice. So, what does that mean my equilibrium concentration is going to be for A? Well, if I start with 1, and then I change by negative x, so it's just going to be 1 minus x. And then what's my equilibrium concentration of B going to be? And C? Okay. Now what we'll do is, we're going to take this information and plug it into our equilibrium expression. Well, it says for A, use k equals 1. All right, fine. So 1 I'm putting in for k. Now that equals, what's my equilibrium concentration of B? X. So x times x divided by, okay, how do I do a solve for x? And of course, you guys have all taken algebra and gotten your A's, right? We can all algebra. So let's algebra. Let's math it. So I guess anytime I have a fraction, it's nice to get rid of fractions, right? So I'll multiply both sides by the denominator. So 1 minus x equals x squared, x times x. And then I guess let's move everything over there with the x squared. So x squared, well, I had negative x, so I guess I'll add x, and then I'll subtract 1. Okay, that's crappy. Are you okay with me doing that much in one step? You follow my algebras? We're mathing? Okay. Man, what does that look like to you?
Looks like x equals plus or minus.
quadratic.
This is a quadratic equation, isn't it?
Do you have any whiteout?
Nope,
There's a curve.
I don't.
Simple things, there's not this.
Yeah, this is a quadratic equation. Now, that means we're taking out this guy. Did you guys have to memorize the quadratic equation? Remember, negative b,
Plus or minus the square root
what's that? B squared
of minus
4ac over 2
Hey, Mr. Downing, why can't we just...
a, 2a.
Yeah. Mr. Downing.
Huh? Yeah, in this one we probably could factor. We could factor the x squared plus x to be x times x plus 1. Yeah. So, are you singing a quadratic equation song?
Yeah.
Hmm.
B squared minus 4ac all over 2a. It's good, Mr. Nichols.
Huh. When I was a kid, they just keep beating us until we remembered it. If you remembered it, they stopped beating you.
They gave us no
I just
clue.
I kind of
You know what, though? I remember it.
Yeah, exactly.
Yeah. They were beating me with love, though. So, if you plug everything in... Well, first, quick review. What's all this ABC nonsense? Yeah, those are the coefficients for x squared x and my constant. So if you put that in, you'll get either x equals negative 1.618 or x equals 0.618. You remember with the quadratic equation you always get two answers? Because it's the plus or minus. So you always have to do it twice, right? Well, that's weird if I get two answers. There's only one equilibrium. How can I have two answers with one equilibrium, though? One of them doesn't work. How do I know which one?
You have to...
I heard someone say it. The negative one is dumb.
It's never the negative one?
Nope, never the negative one.
Can you go back and like unerase it, please?
Why is it not because it's negative? Like, I thought because it's... this isn't talking, but I just want to
Yeah. This happens a lot in chemistry and physics. We get an answer that's real and an answer that's imaginary. But what world do we live in? The real one. Yeah, this is the real world. This is real life, guys.
Are you sure it's not green?
Yeah, pretty sure.
And just to clarify, Mr. Downing, it's not negative because negative would mess up the entire formula.
Well, it works mathematically. So the negative works mathematically in the quadratic formula, but in the real world, It doesn't work.
You can delete
Because the real world, so if this might explain it better to you. If I'm going to end up with X worth of concentration of C, I can't have negative 1.6 moles of C per liter. That's what I'm saying. That's an imaginary universe. That's not our universe. That's an imaginary world. Okay? So does that make sense why we can't have the negative one? Because
So do we even have to find the negative or can we just find the positive?
we only need the positive one. I plugged it into the quadratic equation. So I took these coefficients. Yeah, the 1, 1, and negative 1. Yeah, the A, B, C. Okay. Now, but they didn't ask me to solve for X. They said, find the equilibrium concentrations of A, B, and C. So if X equals 0.618, I'm going to move that over there. What is my concentration of A at equilibrium?
1 minus 0.618?
Yeah. So 0.382 molar. What's my concentration of B?
0.618.
0.618 molar. What's my concentration of C? Yeah, same thing. With me? Okay. And I'll leave B and C for you to practice. They work exactly the same way, except the only difference is that in B, Kc equals 0.01, and so I would go up here, and instead of putting in 1, I would put in 0.01. Otherwise, I'd solve it exactly the same. Yeah, the only difference is B and C uses a different constant for K. All the other numbers are identical. That means I'm just going to solve the algebra a little bit differently. Okay. Well, you know what? I'm not going to do B, but let's do C. C is interesting. C is interesting. Let me tell you why. Let me erase my chalkboard here. Don't worry, you're going to like C. You're going to like it a lot better. How does my K equation look, though? Do I need to change this guy? No, I don't, do I? I have the same reaction, same coefficients. I didn't change the equation. They're just saying, like, imagine this other equation that looks exactly the same but has a different coefficient. So now I'm going to write in red to show C. So now whenever I do this, I'm still going to get the same negative x. I'm still going to get a positive x here. All that looks the same, doesn't it? And whenever I plug in, now I'm going to do 1 times 10 to the negative 5th equals x over 1 minus x. Okay? Well, so whenever I simplify here, I'm going to say that, well, x times x, that's x squared. Okay?
Hey, Mr. Downing,
Yeah.
wouldn't it just be easier to decide just to put 4 zeros in the line?
Maybe. I don't want to. But you could. If you like that, go for it. Right about negative 5 is really about the point where you really start making that decision. But now here's the deal, though. My K is very, very small. 1 times 10 to the negative 5th. When I have a very small K, what does that mean? What does that mean about my products? I'm not going to get very many of them, are I? I'm expecting my x to be really small. What I'm saying is, I'm expecting, let me jump to an ugly color. I'm expecting that 1 is much greater than x. And what does that imply? That implies that 1 minus x equals 1.
Oh.
So what I'm saying is, what makes this really nice is this is now divided by 1. Which means I don't have to do the quadratic equation. All I have to do is take the square root. And I'm done. So now I'm just x equals whatever the square root of that thing is. 0.0036. No, 0.00316. Because all I have to do is take the square root. Much easier than the quadratic equation, right? But here's the problem. How do I know that this is true? Problem is I don't have any idea. I just tried it. But I can check it. Here's what I'll do. Okay? I'm going to check this assumption. I'm going to go and do 0.00316 divided by 1. So, if you're trying to figure out if it was okay to assume this part right here, that you could just cancel out the x, okay, that's the critical part. Because if we can get rid of the x on the bottom, we don't have to do a quadratic equation. So to see if it's okay to make 1 minus x just into 1 and drop the minus x part, we're going to do what the answer for x is divided by whatever we were subtracting by. And whenever you get that answer, we're going to do a percentage, so times 100. You'll get that that's just 0.32%. As long as that comes out to less than 5%, that our assumption that the subtraction didn't matter is valid.
Why does it have to be 5%?
That's just kind of our margin of error. We're saying as long as we're going to get within 5% of the answer, that's close enough. Generally, we're going to get nervous, really, if we get above 4%. It's going to make us nervous. But this, 0.3%, that's saying it's barely anything. It's barely any part of 1. So we don't care. We're saying that our assumption was fine. If we do this assumption check and it comes out to more than 5%, we're going to have to go back. We're going to have to erase all of this stuff right here. We'll erase all that, and then go back in quadratic equation. That's what we'd have to do. But it comes out fine, so good news. No quadratic equation required. So then we're already ready to finish this problem. Because if we know what x is, then the concentration of A is equal to 1 minus 0.00316, which is 0.9968, which is really just pretty much 1 molar, right? Our concentration of A pretty much didn't change. Because my concentration of B, well, and C, that's really 1, and C equals that point, what am I doing? Equals 0.0032 molar. Tiny, tiny concentration. Okay? So the only difference between C and D is C was actually way easier because I made the assumption that 1 minus x pretty much equals 1. Therefore, I didn't have to do the whole quadratic equation. I got rid of all that nonsense, and I just took the square root, and I simplified it real fast. So sometimes you can make that if k is really small. If k is really small, you can make that assumption. If k is not small, you're going to have to quadratic equation.